Right. Well, I guess I should go ahead and get started. Uh, this week's lab, we actually don't have a lab. We supposedly in week one we did intro to lab, and we did. That was on the week of January 12th, and then the week of January 19th. That was Martin Luther King Day. I had scheduled on my syllabus that we not have a lab that week, just because we try to keep all of our labs in order, even if they're online, with our face-to-face labs. And since we had to miss Monday, that meant nobody could have a Monday lab. And that meant you guys who have lab technically on Thursday now, you don't have a lab. So we ended up going ahead and doing the second lab, which I think was motion detector or something along those lines. I'm pretty sure it was motion detector. And because of that, we're actually ahead. And last week we did introduction to Excel, so we're done with that. The very next lab we're supposed to do is linear graphing one, but I also like to fit in my 241 semester. I like to fit a propagation of error lab. So what I've done is I've taken this week's lab module. It says week five lab module, February 9th to February to 11:59 p.m. February 15th. In that lab, I've put in my propagation of error video as well as my other propagation of error videos. So there's two videos on doing a propagation of error lab. They're in my week five lab module. Then there's the propagation of error document. It says lab four, I think, propagation of error uh, 1.5 docx or something like that. That is a document that I wrote up to teach you guys how to use uh, propagation of error rather than sig figs. So what I'm asking you guys to do in lieu of a lab report this week is watch that video and read over that document and see if you could actually start filling it out, because there is going to be a point at which we turn that in as a lab. It may turn out that 2 weeks from now I hold a lab and I ask you to do that in addition to one of your regular labs. So by giving it to you now, you just have more opportunity to slowly read it and make sense of it. What you're trying to do with that lab is you're trying to read it, make sense of it. Then you're trying to fill in not the first table, because the first table is already filled in, but the exact copy of that first table is in this is a little further down in the document, and that one hasn't been filled out. But you're expected to fill it out, and unless I made an error, uh, all the things you fill in should be more or less exactly what was in the table that's already filled out. So it gives you a goal to shoot for so that you can check, make sure you're doing it correct. And as I said, there may be an error in it that I may have made some careless mistake. Maybe I divided by seven when I was supposed to divide by six, or maybe I forgot to add the one or some goofy stuff like that. The main thing is I want you to be on your toes, looking for any errors I might have made in filling out that form, and then you fill out your own. Uh, Once that's ultimately done, you've more or less completed a major part, which is the ability to use either well, in this case for the table, you're actually supposed to use that by hand. You're not supposed to actually use that via Excel. You can later use Excel, but the main thing is you're doing that table by hand, and then you're supposed to, in the very next question on the module, or on the lab report, you're supposed to then use your calculator statistics function. Or if you can't figure out how to use your calculator statistics function, maybe you don't have the user manual anymore. Maybe, uh, really, to be honest with you, not having the manual is not an excuse. You can actually Google the type of calculator you have, or do a search for it on YouTube, and you'll find someone teaching you how to do the statistics with that particular calculator. So by all means, you still can do it. But if you're unable to find a way to do it with your calculator, or your calculator doesn't have a statistics package, which actually I doubt, uh, then your job is to do it with Excel. But if you do it with both Excel and your calculator, I'll give you points extra credit. The main thing is I want you to verify that the calculations you do by hand are exactly the same results that you get when Excel does it, are exactly the same that you do when your calculator does it. And then there's also some additional questions where you're using this idea of a partial derivative, which is normally beyond the scope of this course because this course, Physics 241, requires Calc 1, and partial derivatives usually don't come up until Calc 3. But as I warned you guys over and over again, when you're in physics or science or engineering, almost always you're going to learn your mathematics from your physics math or engineering or chemistry instructor well before we get to your what your math teacher teaches. So yes, I did say math. That was an accident. Specifically, what I'm saying is you're always going to learn new techniques in mathematics in your physics or chemistry or engineering or, classes well before you learn them in your math classes. Even if you take the appropriate math classes, they're not necessarily geared the right way. Like for instance, I took differential geometry, and literally the last day of the semester was the first day we covered differential. Excuse me, we covered covariant differentiation, and literally that's like the first thing you do in general relativity. So, if you had differential geometry, which is one of the underlying mathematics of general relativity, you could take a whole semester of that and just barely get to the first thing you do in general relativity. Whereas if you took general relativity, you're going to learn differential geometry, specifically the covariant derivative, immediately, like literally the first or second day. So, so that's the way things happen with regards to learning mathematics in a science or engineering field. So, with that in mind, you're supposed to be able to do a partial derivative to do the propagation of error. The good thing is a partial derivative is really very simple. It's no more complicated. In fact, it's a little less complicated in some sense than regular differentiation. So, for instance, you're used to in regular differentiation taking a derivative of f of x equals x squared. Obviously, that's x to the n, and the derivative of x to the n is n times x to the n minus 1. Well, what if I instead had f of y times z times x squared? Well, if you take the derivative of that with respect to z, or excuse me, with respect to x, then you're going to get 2xy or 2zy times x. In other words, you're just pretending like the y and the z are just constants. So if you had, for instance, instead of y equals x squared, which is what the original function was, and the derivative was 2x to the 1 power, if you try to take the partial derivative of instead of x squared, what if you took the derivative of 2x squared? Well, the derivative of 2x squared would just be 2 times 2 before x squared, or you'd say 2 times 2x. That's what would happen if instead of 2 you had y equals, or f of x equals zx squared. You just treat the z like a constant, so it would become 2zx. And if the function was zx squared plus y, the partial of that with respect to x would be 2z x. And then since it's plus y, the y is a constant. When you take the derivative of a constant, you get zero. So that's all you have. In other words, you completely dropped off the plus y when you took the derivative. So that's really what the partial derivative is. And I will teach this more if we do manage to fit in the propagation of error lab later. I just wanted to give you a little bit of a heads up. But after I've talked about that and talked about how you do a partial derivative and given you examples, I then ask you to implement those exact same examples as well as some other ones on your own to derive formulas for propagation of error. So all of this lab is specifically about a tool that real scientists use when we deal with numbers that have error in them. And of course, all measured numbers have error in them. So anytime you make a measurement of a quantity, then you record that quantity. You need to know not only what the answer is, you need to know its units, but you also need to know how much the error is. So, for instance, if I told you that the after a series of experiments, I measured the width of a rectangular box. Okay, that width might come up to 15.10 plus or minus 0.03 centimeters. So that 15.10 is the best estimate I got from all the trials of measuring that width. Now, that best estimate, if you really had access to everything, that best estimate might be a weighted average that you computed from all the trials, where you weighted each trial based on how good the experimental technique of that particular lab person was. And you can do that by, instead of just taking the numbers, 15.06, 15.71, 15.15, whatever, instead of just taking those numbers, you're going to take those numbers and divide it by the square of the error of that particular lab participant. So, for instance, if one lab participant was really, really good, his typical error in measurement might be zero point zero 0.02 centimeters. Then what you do is take his measurement, which might be 15.07, and you divide that by zero point zero 0.02 squared, and that makes it like a weight for the 15.07. And then you do the same thing for any other person. Take their result and divide it by the square of their error. And as you see, if the error was really small, like zero point zero 0.01, then you dividing it by the square of zero point zero 0.01 makes it like that particular value has more weight than the other ones. Whereas if you had a particular lab participant whose error was point zero 0.09, well, that's a particularly big error. And when you divide by 0.09, you give that very little weight. So that's how you would implement a weighted average. You would do the value divided by the square of the error plus the value divided by the square of the error plus the value divided by the square of the error for however many participants you had. And then you would normally, of course, want to take that, since it's sort of like a weighted average, you would want to take that and divide it by all the sum of all the weights. Well, the sum of all the weights is 1 over the first person's error squared, and then the sum of, or the next person's weight is 1 over that person's error squared. The next person's weight is 1 over that person's error squared. So you're going to take in the denominator and take 1 over the first person's error squared plus 1 over the second person's error squared plus 1 over the third person, and keep doing that until you've exhausted all the percentage or all the errors, and then what'll come out is the weighted average. Now, that is the or a good true way to do a weighted average, but in our lab we never have the complexity or the hierarchical structure to allow us to do a weighted average for a single measurement like the width of a meter stick or the width of a rectangular solid or anything like that. So we just default to just the average. Okay. So the average, which means, the first measurement plus the second measurement plus the third measurement, dot, 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 plus up to the, let's say, the 25th measurement. Then we divide all that by 25. That gives us the average of all our measurements. So that's our best estimate. And that's what goes to the left of the plus or minus when we report the width of the rectangular box to be 15.10 plus or minus zero point zero 0.03 centimeters. The 15.10 would be the mean, and the plus or minus is followed by zero point zero 0.03 centimeters. That zero point zero 0.03 is a quantity that we need to calculate as well. That particular quantity in the practice of experimental physics and other experiments is supposed to be our standard error. Now, the standard error can also be called the standard deviation of the mean. And when you read the document, that'll make more sense to you. But again, it's not going to make all that much sense unless you do a lot of research or you wait till I give you a full description of it. But the main thing is what you're going to do is you're going to learn how to calculate that. And the way you calculate that is you first calculate the standard deviation, which is the difference between a single trial and the mean. So let's say one of your trials was 15.07 and the mean was 15.10. So you'll do 15.07 minus 15.10. And if you actually took the average of those, that was called a deviation. The difference between the trial and the actual mean is called the deviation. If you took the average of those deviations, that would turn out to be zero, so it's not very effective, not very helpful. What we do instead is we take the average, in some sense, of the square of the deviations. That way, the negative values don't automatically cancel out the positive values and give you a average of zero. So instead, what we do is we do 15.07 minus 15.10. We'd square that, and then we take the next trial, which might be 15.11 minus 15.10. We square that, and then we keep doing that for all the trials until we've got the sum of all the squares of the deviations. And then what you would want to do is divide it by normally the number of trials we did. But what we've learned is that when our number of trials gets really small, the statistical results and statistical tools that we use do not work very good. They work best when we're dealing with hundreds or even thousands or tens of thousands of trials. So to correct for having such a small number of trials like 5 or 10 or even 25, we divide instead of by n, the number of trials, we divide by n minus 1. So it turns out when you're actually dealing with really big numbers like n equals 10,000, then n minus 1 is no significant change from just plain n. So it's perfectly fine to do that. The other problem though is we now have a quantity, and for instance, in the standard deviation, the deviations that we were calculating, each of those deviations had units of centimeters, but then we squared them, so that gave us centimeters squared. Uh, that quantity, the average of that quantity, even dividing by n instead of n minus 1, that does not have the right units to be put after a plus or minus because you can't add it to the 15.10 because its units are in centimeters squared instead of centimeters. So the final step, in addition to taking the deviation squared plus the second deviation squared plus dot 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 on up to the nth deviation squared and dividing by n minus 1, in addition to that, you now have to take the square root, and you can sort of think of that as getting it back to the appropriate units. That formula, the square root of the numerator under the radical summation from I equals 1 to n of x sub I minus x bar, parentheses squared, divided by n minus 1, in still inside the square root and under the fraction bar. That is the formula for standard deviation. Now, the standard deviation of the mean is sort of like going through that same process, but you're doing it with the means of, let's say, a bunch of sub labs. So instead of imagining individual people doing measurements, imagine that you have host of labs all over the planet. Okay. And then each lab had associated with it a certain error and all that good stuff. Well, now instead of taking individual trials, you're taking one of your labs best estimate for the width of that box, and you're treating that as a mean. And now you're going to take the best estimate for your second lab and treat that as a mean, and the best estimate for your third lab and treat that as a mean. Now your idea would be to calculate the standard deviation of that, and that is the standard deviation of the means, and that's also called the standard error. And it turns out the formula for that in total is really just taking the standard deviation that we already calculated and dividing it by the square root of the number of trials. So S over the square root of n is the standard error when the standard deviation is S. Okay, so that's the actual number. That standard error is the number that comes after the plus or minus when you report a measured result. So when I say the box has a width of 15.10 plus or minus 0.03 centimeters, the 0.03 centimeters is one of two things. If the instrumental error, let's say you're using a meter stick, therefore the instrumental error is probably 0.02, 0.03, something like that. If you wrote down when you first started making the measurements of the width of the rectangular solid, if you wrote down the instrumental error for your measuring device was 0.03 centimeters, okay, then that's fine. We need to have that record of the instrumental error. But now, once you do all those statistics, so you calculate the standard deviation and then you calculate the standard deviation of the mean, i.e. the standard error. If the standard error came out to be 0.02, but the uncertainty in the measurement or the experimental or instrumental uncertainty was 0.03, then you have to use the 0.03 because there's no amount of statistics that can compensate for the imprecision of your device. So if your the device can't measure any better than 0.03, and the statistics tell you that the difference is zero point zero 0.02, then the difference isn't the error isn't zero point zero 0.02, the error is zero point zero 0.03. Okay, so it's always the bigger of the two, the instrumental error versus the calculated standard error, which is also called the standard deviation of the mean. Okay, always, always, always. So every time you make a measurement, you have to first estimate what the uncertainty of that measuring device is. As I said, for a meter stick, it's at least zero point zero 0.01. Uh, I would argue that I can't tell the difference between 15.03 and 15.04 centimeters. So I would say the error is not plus or minus zero point zero 0.01. In that case, I'd say maybe the error is plus or minus zero point zero 0.02. Okay. If you're doing weird things like maybe you're measuring something that's not a perfect rectangle, then one width is a little bit different from another width, different from another width, different from another width, like that. That's a whole other reason to assume that there's some error in it. But if worse, if there's like some gap between the measuring device and your ability to see the thing, so you sort of got to approximate where it's lined up with, then that builds some error, and you might want to bump up the error from zero point zero 0.02 to zero point zero 0.03 or something. All of that's fine. That's completely objective for you, but it might in other people's eyes seem subjective. That's okay. The main thing is you're trying to use your most honest assessment of what the uncertainty of that measuring device is, and you write that down. Then, with no judgment whatsoever, and you could write down as many sentences or paragraphs or whatever to explain exactly how you come up with that error, that would be perfectly fine, and that's a good thing to do. But once you do the statistical analysis and you find that the standard error is bigger than that quantity, then you use the standard error. But if you do the statistical analysis and you find that the standard error of that quantity is lower than the instrumental error that you determined, then you're going to have to use the instrumental error. If you're dealing with something that's like a digital readout, then best case scenario, it's plus or minus one in the last digit. That's the instrumental error. If you open up the user manual, it might actually give you a real value of what the error is of that measuring device. Then you're supposed to use that. Okay. But if you don't have that, then you always assume it's at least one in that last decimal place that it displays. So, for instance, a voltmeter might give you a voltage reading of 1.42 volts. Well, the fact that 1.42 has been reported tells you that it's good to two decimal places, and that would be, of course, to the hundredths place, and therefore you would assume the uncertainty is zero point zero 0.01 volts because one in the last decimal place is zero point zero 0.01. So that's the best case scenario of the instrumental uncertainty. But if you open up the manual, you might find that it's plus or minus zero point zero 0.02, in which case you should use that. All right. Now, once you have, a certain number of quantities that have been measured, like the length, the width, and the height of a rectangular solid, okay, what happens to the error of those numbers when you use them in a formula? That's what propagation of error is about. So when you take the length, which might be 7.29 plus or minus zero point zero 0.07, and you take the height, which might be 2.89 plus or minus 0.05 centimeters. If I want to calculate the volume, I take the best estimate, the 15.10, the 7.29, the 1.38, whatever is to the left of those plus or minuses. I multiply length times width times height using those values. That's my best estimate of the volume. Now, how do you go about figuring out the actual uncertainty in that volume that you calculate? Well, that's what the propagation of error is for, and we give you a formula for that. That formula is the uncertainty in a function f is equal to the square root of the partial derivative of f with respect to, let's say, w squared, that whole derivative squared, times the uncertainty in w squared, plus, now I take the partial derivative of f with respect to length, and I square that, multiply that by the square of the uncertainty in L, and then I say plus, and now I take the partial derivative of f with respect to the height. I square that derivative and I multiply it by the uncertainty in h squared, and then I finish off the square root. So the square root of the sum of the squares of the product of the partial derivative and its error uh, basically is the formula that you use. If you have a function that's just one variable, then the uncertainty in f is the absolute value of the derivative of f with respect to that one variable times the uncertainty of that variable. Okay, all of these formulas are listed in there, and I explain them in the wording of the propagation of error document. But the main thing is, I wanted to give y'all a little bit of a idea about that. Well, it turns out when you use that propagation of error formula, if you repeatedly analyze functions that are just multiplication and division, like f of x, y, z equals x times y times z. Well, it's always going to turn out that the fractional uncertainty, and that's the uncertainty in the function f divided by the function f itself. That fractional uncertainty is just going to be the sum of the square, or the square root of the sum of the squares of the fractional uncertainties of the individual variables. So if the function was f of x, y, z is equal to x times y times z, then the fractional uncertainty in f would be sigma f over f, and that would be equal to the square root of sigma x over x, parentheses squared, plus sigma y over y in parentheses squared, plus sigma z over z uh, in parentheses squared. That would be the fractional uncertainty of f. And if you wanted the actual uncertainty of f, you just take that fractional uncertainty and multiply it by the actual best estimate of f, and that'll give you the uncertainty in f. Well, that seems to be true, that sum of the squares of the fractional uncertainties is true whenever all your variables are either multiplied or divided. So I got that for f of x, y, z equals x times y times z. But if you did f of x, y, z is equal to x times y over z, you get the same result. If you did f of x, y, z is equal to x over y times z, you get the same result, and so on and so forth. So whenever you multiply or divide the sum of the squares of the fractional individual uncertainties, take the square root of that, and that's the fractional uncertainty. However, if you happen to just be adding and subtracting, like f of x, y is equal to x plus y, or f of x, y is equal to x minus y, or f of x, y is equal to, well, there's some other ones too. The main thing is when you do that, it turns out that that the actual uncertainty, not the fractional uncertainty, but the actual uncertainty of f is the sum of the squares of the actual uncertainties of x and y and so on. So if you had x plus y plus z, the uncertainty in f would be the square root of the uncertainty in x squared plus the uncertainty in y squared plus the uncertainty in z squared. Notice I'm just saying uncertainty, not fractional uncertainty. That's the difference between all your variables just being added or subtracted versus all your variables just being multiplied or divided. When they're multiplied or divided, you're going to get a fractional uncertainty that you have to square and put under the square root. When you're doing adding or subtraction, you're just doing the regular uncertainty that you're going to have to square and add under a square root. All right. So as you read that document, you can go ahead and start that. This is actually a fair, even though I didn't take time to write it out on the board. If you can manage to listen to this while you have this document open, and then follow through what I'm saying, ideally what you'd want to do is first read the document. Even if it doesn't make much sense, just try to read it through. Not necessarily in one setting. You always want to try to read as far as you can till you lose your attention span, and then stop, take a break, come back and read for that same amount of time again, and then stop, take a break, read for that same amount of time again. Do that, maybe 5 to 10 times, then try increasing that length by about a minute and do it again. And then after 5 or 10 times, increase it by another minute, do it again. But once you're done, after one whole cycle of completely reading that document, then come back, watch this video, and follow along in the reading. When I mention something on this video, look for that section, pause the video, look for that section in the actual document to make sure you know where I'm talking about, and then reread reread over that section and then listen to what I say about it and then reread some more, listen to what I say about it, reread some more, listen to what. By doing that, you'll have a better understanding of the document in its entirety. Now, again, when I actually do decide to assign this lab, you'll have been way, way ahead of time. You'll already be starting to understand this stuff. It'll all work out a lot better. And then I'll just come in and explain it, and it'll seem a lot more trivial than it does right now. Right now, it probably seems scary as poop. So I apologize. That just is a nature of it. And I got to admit, the first time I had the first time I learned this propagation of error stuff, it took me by surprise too. And I'm really, for a bit there, I started thinking, well, maybe I shouldn't major in physics. This is way more complicated than I remember. So don't feel bad. That's a normal response to people when they're learning new branches of science, mathematics, probably everything. It's just I haven't learned at such a high level with literature or history or some of these other subjects, economics or psychology or whatever. So keep that in mind. That's just what I've learned from the science standpoint is just continually trying ultimately does pay off. So that's it. I'm going to go ahead and let you guys go. Again, there is no lab due this week. Your job is to start watching that video. If you can actually afford the time to watch it now, one of those videos or both of those videos, I'd say do it. And then if you can afford the time to read that document, it'd be better to read that document first, then watch the video, then read the document again, then maybe watch the second video, then read the document again, and then wait for me to give you a presentation, or go ahead and start doing the document, filling out the answers and that sort of stuff right now. I suspect you can do all that without ever having any more from me. Okay, but I am going to give you a more thorough instruction on this later. So thank you everyone for coming. I did not get a huge number of people that replied to my last message where I sent out an announcement and had a little cut and paste thing where you're supposed to tell me how many of you can show up at 10 a.m. on Tuesday, how many of you can show up at 11 a.m. on Tuesday, how many of you can show up at 12 a.m. on Tuesday, how many of you can show up at 10 a.m. on Thursday, how about 11 a.m. on Thursday, how about noon on Thursday, and so on and so forth. All of you were supposed to send that to me, and I only got a few people that sent it. So I really need that. Please get back to me ASAP. And this week, what I'm going to do, since I didn't get that many people to respond to me, I'm going to go through to everybody that did respond to me, and I'm going to go send an email and just let you all know that I did get it, so you know, oh, okay, Mr. Younger did get mine. I don't have to send it again. But if you don't get that, that means you didn't send it or I didn't get it. So uh, I'll call it a day. It's only been about 30 minutes. You folks are free to go. I will try to sign in again today at 5 p.m. for my 242.005B class. But remember, from 5:30 to 6:50 is when that online class meets. But from 5 to 5:30 on Thursdays, I come in at 5 so you guys can have an office hour. That's for your class and all my other classes. So by all means, feel free to show up at that as if you're going for the 5:30 Thursday afternoon class, but show up as early as 5 if you'd like, because I'll be there. Thank you for coming, everybody. I hope you have a great weekend. Stay safe. Remember, we do have an online test that was due Sunday at 11:59 p.m., but I've now moved that back to Tuesday at 11:59 p.m. That's on chapters 3 and 4, but all my tests are comprehensive, so that means it's on chapters 1, 2, 3, and 4. I finished the topic of chapter 4 last night, even though there's plenty more examples you should do, and I specifically asked you to go to my YouTube channel and do a search for fuzzy Fuzzy, and you'll find a fuzzy dice problem. That one is sort of the last example from chapter 4 that I wanted to cover for you. I just ran out of time. The main thing that that one teaches you, in addition to learning how to solve that problem, is it shows you a neat new way of solving systems of equations that I'm pretty sure your math teachers rarely told you about. And that's because there's always a danger. You guys know that when you went through pre-algebra and then algebra 1 and algebra 2 and all that good stuff, you learn never divide by zero. So guess what? If one way you can solve a system of equations, if they have the right form, is you can divide one of the equations by the other equation. You can see why your math teacher wouldn't teach you that, because if that equation ever turns out to be the left side zero or the right side zero, then division by zero would give you an erroneous answer and you wouldn't even know it. So it's really, really dangerous. But as long as you know the limitations and know, hey, this is not going to be valid if I deal with a case where this denominator in this division problem is zero. As long as you know that accordingly, then you can still use that technique. And that's what we end up doing. We end up using the technique to divide one equation by the other. That eliminates one unknown and allows you to solve for the other unknown. So make sure you guys look over that example and understand it. With the Atwood machine, where I showed you how to add the left-hand side of one equation to the left-hand side of another equation and set that equal to the addition of the right-hand side of one equation to the right-hand side of the other equation, that was a new technique we learned for solving systems of equations, but hopefully that was one you'd already seen in your math classes before. Now I've given you another one where you can divide one equation by another, so that rounds out your toolbox for right now. So have a good weekend, everybody. Thanks for coming, or thanks for taking time to watch this. Bye bye.